Example 5.4. A ray is incident at point A. Then the refracted ray is critical at point B and reflects to point C and then refracts. The image is not scaled properly. A. Draw an accurate ray diagram for the situation. Calculate the index N3, the angle θ1, and the refracted angle at point C. If θ1 is decreased, does light refract into medium 3? Will the refraction at point C ever be parallel to the boundary? A. Let's draw an accurate ray diagram for the situation. So what I'm going to do here is that I'm going to use the image that's given to save time. So only part of this is going to be accurate. Okay, so now let's look at the ray at point A. There's going to be some refraction. And so this here is the ray that is unrefracted. Now, if I look at my normal, I have a normal here. And note that the normal at B here is not the same orientation as it is at point A. And I could say the same thing for the refraction at C here. So the normals have different orientations, and that really changes how Snell's law looks here. So now let's look at that. So this is accurate. So look at that. I'm going from index 1 to index 2. You can see I'm going from a higher to a lower. So there should be bending away. So here I go. So if I look at my ray here, it's going to do what? It's going to refract away, and it's going to go from A to B here. So when you look at that, look what happens. This is bending away. Right? So the first thing that I should say here is that since N1 is greater than N2, the ray bends away from the normal at A. No surprise. Now what they're telling us here is that the ray is critical at point B. So if it's critical, that means here that the ray has to be parallel to the boundary. So when I measure this angle right here, at the critical point, this is 90 degrees, right? So this is the refracted ray into medium there. Now note, there's going to be another ray, and this one's going to be, I'm not going to scale it too much, but this guy here has to be the reflected ray. So now let's look at this thing here. So if I look at this, what am I seeing here? I have a critical angle at A, implies the refracted ray is parallel to the optical boundary. And this angle, maybe a good would be to call that 2-3, which is 90 degrees right there. Okay, so now let's start following the basic geometry here. So now let's look at this thing. No, maybe I'm not going to do that just yet. So all I know is that if this is the critical angle right here, then that guy has to be the critical angle right there. And I call this angle here theta 2, 3. So let's not get into the problem solving just yet. Let's just make a good ray diagram here. So now what I'm going to do here is that I'm going to focus on the next piece. So the reflected ray at A has the same angle as the incident ray. And in this case, it's theta 1. Here's where it's not going to be accurate. So in order to make this work, and we're not really interested, I would have to draw it pretty far down and the picture would have to be quite big. So look what I'm going to do. I'm going to mess around with this and look what I'm looking at. The ray comes like this, and that's the unrefracted ray. So what you're seeing here is that here's where I'm going to change the picture, and I'm going to say this angle here is theta 1. Obviously, it's not the same angle. And this is the dashed line is the unrefracted ray. Now look what's going on here. N1, so if you look at this thing, we could say this. If N1 is greater than N2, then N2 must be greater than N3 to have total internal reflection. So this immediately tells us that N1 must be greater than N3. So that means here is that this ray is refracted away from the normal. So that means here, if I pick a different color for the ray, that means that this ray has to be going like this, right? And you could see that this guy is moving in that direction, and it's moving away. So now I'm going to define this angle relative to the normal. I'm going to call this theta of 1, 3. So now my job here is to take this picture and calculate all of the quantities here. So let's go do that. So now I would say that's an accurate picture. So now let's go to B. In B here, there are 3 quantities that need to be calculated. That is N3, theta 1, and theta 1, 3. Let's go do that. Okay, so the first thing I'm going to do is I'm going to start off with index N3. So all we know is that light is critical at point B. So that means here, it means this here. So light is critical at point B. Okay, if it's critical at point B, what does this mean? So now let's draw our picture again. So what we're seeing here is that I have the following thing. I have a boundary that looks something like this. You know what? I'm going to bring it down a little bit. And so now we need to start looking at our picture here. So this guy right here is our green boundary. This is our blue boundary right here. And then this is, of course, our yellow boundary. So now what am I seeing here? At point A, I know I have a ray that comes in. So now let's look at our normal. So our ray comes in like this. And this angle is theta 1. So then what happens is that this guy gets refracted away. And so what we'll do here is that we're going to define this angle as theta 2 according to Snell's law, but this angle is also theta 2. So if I put in my normal right there, note that I have a ray that goes like this, and we already saw that this angle is 90 degrees. And just again, note that this is N2, this is N3. And so what I'm seeing here is that the angle that we're really thinking about right here is this angle here, which is theta critical. Now, here's what you want to look at here. Because the normals do not have the same orientation, right? If you look at the one at point A, look what happens here. At point A, it's vertical, but at point B, it's horizontal. So you're going to introduce a 90-degree change. So what you're seeing here, the critical angle is theta critical, which is 90 minus theta 2 here, right? Just using the angle relationship. So now, if I apply Snell's law, look what I see here. So at point B, Snell's law at point B, here's what we see. We see that it's going to be N2 sine, and this is going to be 90 minus theta 2, but this is the same as N2 cosine of theta 2, which will then be N3 sine of 90. So this tells us here is that N3 is now N2 cosine of theta 2. So if we solve for theta 2, we then know what the index of refraction for medium 3. So here we go. Now note that so if you look at this thing, note that we know two sides of a triangle. So let's go back and look at this thing here. So what this is telling us is that we have two dimensions. We know that this dimension right here, this is 5.77 centimeters, and then this distance here is 10 centimeters. So what I'm going to do here is that I'm going to use geometry to calculate theta 2. And so what that means here is that I really have a triangle that does this, right? Here's my triangle. This is theta 2. I know this side, and I know this side. So then this tells me here that the tangent of theta 2 is going to be 5.77 divided by 10. So then theta 2 is going to be the tan inverse of 0.577, which gives me 29.98 degrees, which I'll call 30 degrees for theta 2. Now that I have theta 2, I can now calculate the index N3. So now N3, which is now N2 cosine of theta 2, is then going to be 1.60 cosine of 30 degrees, and that gives me 1.39 for index 3. Okay, so now we've calculated that. Now that we have that, let's go calculate the angle theta 1. So now that I have theta 2, I'm just going to apply Snell's law at point A. So that's going to be a fairly straightforward calculation. So I'm going to apply Snell's law at point A. And this is the interaction between the two mediums. So here we go. So we see that N1 is going to be sine of theta 1, which is N2 sine of theta 2. But sine of theta 2 is 30 degrees, which then gives me what? So then I'm going to then solve for theta 1. So theta 1 here is going to be the sine inverse of N2 sine of theta 2 divided by N1. So if I punch in my numbers, right, I know that this is going to be what? This will be sine inverse. This will be 1.60, the sine of 30 degrees, divided by 1.70, and my numbers indicate that this is 54.9 degrees, and this is theta 1. Okay, so now the next angle we got to calculate, it's the angle theta 1, 3. So one of the things that if you look at theta 1, 3 angle here, note that again, there's this change in orientation. So you should expect a cosine term to show up. So let's go draw this so that it's clear for what we're looking at right now. So here we go. So since the normals do not have the same orientation, expect a cosine instead of a sine in Snell's law. So let's draw our picture here. So I'm going to look at my boundary here. And then here's my yellow. So here's what I'm seeing here. And then come in like this. So this is point A. So if I look at point A, here's my normal right here. So this guy comes in at an angle of theta 1, and then it has to reflect at the same angle here And this point right here is then going to be C. So if this angle is theta 1, and we know that N1, and if I compare N3 is less than N1, we know that this guy here has to bend away from the normal. So according to what we said before here, this guy has to bend in this direction. So this guy here, this is the angle 1, 3. So let's keep playing around here. So if I keep doing this, note that this angle right here is also theta 1. So this angle right here, this is going to be 90 minus theta 1. Now I can apply Snell's law. So Snell's law shows that N1 sine of 90 minus theta 1, again, N1 cosine of theta 1 has to equal N3 sine of theta 1, 3. So now solving for theta 1, 3, we see that we're going to get theta 1, 3 is then going to be the sine inverse of N1 cosine of theta 1 divided by N3. So if I now punch in my values here, I get 1.70 cosine of 54.9 degrees divided by N3, which we calculated to be 1.39. And the value that we get here is we get 44.7 degrees for theta 1, 3. So now we have all our angle calculations. So let's come back up and look at what we're doing here now. So we've done A, we've done B, so now let's look at C. If theta 1 is decreased, does light refract into medium 3? Will the refraction at point C ever be parallel to the boundary? So let's go write this out. So now we're looking at C. And C says this. So if theta 1 decreases, what effect does this have for the rays at points B and C? So let's draw it out. So what I'm going to do here is that, again, I'm going to have to draw this guy out again. So if I look at my mediums, it's looking like this. I have this. And then I have my third medium right in here. So now let's go look at these guys. Clearly this is N1, this is N2, and then this guy is N3 over here. So now let's see what happens. So here's our normal. And now let's see what happens. So if I have a ray that comes in, and this is theta 1 here, what we said here is that now I have a refraction that goes to point B, right? This is point B. So now let's look at what actually happens here. Okay, so if theta 1 decreases, look what happens to theta 2. if theta 1 decreases, right? So that means what we're really doing is that we're moving it in that direction. That's what we mean by decrease. And if it decreases, note that this ray, which is theta 2, has to also decrease. So if theta 1 decreases, then theta 2 also decreases. But wait a minute. This here is this angle here. That angle right there is 90 minus theta 2. So then this implies here is that 90 minus theta 2 increases, right? It starts to increase. As theta gets smaller, it goes towards 90 degrees. And if it increases, that means that then theta minus theta 2 becomes greater than the critical angle. And if it's greater than the critical angle, that means that you get no refraction into medium 3. Now let's look at C here. If I look at C, again, the ray, I'm going to have to mess up here because it's not really scaled properly. So again, let's look at this ray. So this ray comes in, and look what I'm saying here. This is the angle theta 1. But this angle is decreasing, right? So that angle decreases right there. So if I now look at this thing, here's what I'm seeing here. So this point right here is the point C here. So if I'm looking at this thing, if theta 1 decreases in a very analogous way, then this angle right here, that's 90 minus theta 1. So what happens? That ray, as this thing gets smaller and smaller and it approaches 90 degrees here, you're going to see here is that that ray starts to move towards the boundary, but it doesn't. Let me make sure here. No. That ray now moves towards the normal. As theta 1 gets smaller and smaller and smaller, that goes towards the boundary here. And so what you're seeing here is this, is that if theta 1 decreases, then 90 minus theta 1 increases. And if it increases, you're going to find here is that no internal reflection will occur. And at some point, if theta 1 goes to 0, then it becomes incident perpendicular to the surface, and then it just goes straight through.